All right, this is the final virtual lecture for EAPS536. The topic today will be tropical cyclones, aka hurricanes or typhoons, depending on where you are. I don't have any specific reading for this. We're going to cover a lot of ground on this topic, as this is near and dear to my heart in particular. And there is a couple of tropical cyclones over the North Atlantic Ocean right now in the movie that we've been playing at the beginning of each of these lectures. Learning outcomes for today are to describe the basics of where and when tropical cyclones form on Earth, explain the physics that make a tropical cyclone work, and explain how both dynamics and thermodynamics govern tropical cyclone behavior on an Earth-like planet. Okay, we're going to start off with some really simple satellite imagery of tropical cyclones in our climate system. This is from the beautiful GOES 16 visible and infrared satellite, very high resolution in space and in time. And this is from 2017. You're seeing hurricanes Katia, Irma, and Jose in the Western Atlantic Ocean. Katia has since moved off, is in the Gulf of Mexico. And you see what you're really seeing in the whites are the cloud tops. So you're seeing the cloud tops associated with these circulations, which are pretty remarkable. I'll play that one more time. And so you can see the kind of circular symmetry of these systems. There's that dark spot at the center is the eye, where you're actually seeing down to the ocean surface. There's no clouds at all there. And so and surrounding that is this dense layer of clouds and strong deep convection and precipitation. And then, yeah, and you can see how that fits in with other phenomena in the region. And then we can also just have a zoomed in view. This is Hurricane Irma passing just north of Puerto Rico, where again you see that eye very clearly. The very, very heavy convection and the cloud tops. You're seeing thick cloud tops around the eye. So it's caused a lot of damage in Puerto Rico, as I'm sure many of you knew, as well as in Florida. Then here's another movie from that same time frame where now you really get to zoom out and see the whole world, which is a different projection, but gives you a different sense. And here I think you get a much better sense of how these tropical cyclones fit in with kind of the broader circulation systems all around the world, both in the tropics where you see this kind of pulsing concentrated regions of deep clouds, very bright cloud tops, indicating that they're very cold because they're high up in the atmosphere, and then the more of the swirls at higher latitudes associated with the extratropical cyclones and other baroclinic eddies, and then kind of a lack of clouds in the subtropics in between, which is pretty cool. So, tropical cyclones on Earth. Here's a map of the distribution of mean sea surface temperatures from 2000 to 2008 in degrees Celsius, and the colors. And then the green dots denote the genesis points of tropical cyclones globally, and the black lines denote the tracks, also from 2000 to 2008. So you can imagine a storm forming at one of these green dots and then moving along the black line associated with it. And so generally tropical cyclones on Earth, you'll notice, form over relatively warm water in the tropics and not at the equator, though. So there's a couple of dots that are pretty close to the equator, but generally you can't be at or too close to the equator. They move poleward and westward with time, usually. So there's actually, I put the arrows, these characteristic arrows on here. There's one region just to the east of Australia that behaves a little bit differently. And then after a while, they recurve with and get caught up in the jet stream, and they die over land or over colder water. So both of those things, the jet stream and the land or colder water, are all bad for the tropical cyclone, as we'll learn. So that's why they generally die as they move into higher latitudes. So on average, there are about 90 tropical cyclones that form each year globally. So this is a time series You can ignore the shading and just look at the lines of going back from 1970 through 2015 on here. Is the count and the number of tropical storms is the curve on the top, which is generally storms. I won't go through the Saffir-Simpson scale here, but you're welcome to just look it up on Wikipedia for how we classify storm intensity. So tropical storms is having a maximum wind speed of greater than 34 knots somewhere in the storm. And so, yeah, so we have about 90 tropical cyclones that form each year globally. You can see some variability with time. It's actually a relatively steady number, maybe potentially a slight decrease towards the end there, but in the last, say, 20 years. But so what I'll focus on here is, so I said, there's about 100 tropical cyclones. So why not 10? And why not 1,000? Why is it 100? We actually don't really know why. It's an active area of research. So tropical cyclone activity generally peaks in the late summer. So this is a plot showing, so the x-axis is the month, the month number from 1 to 12. And the northern hemisphere is the first set of numbers, goes from January to December. And then the southern hemisphere is just shifted by 6 months. So the southern hemisphere, starting in the southern hemisphere winter, is July through June. And then the y-axis is count in the number of Genesis events per month. And you'll notice that the curves look very similar. The northern hemisphere clearly has more storms every single month throughout the year, especially during the primary tropical cyclone season. And so the main thing I'll highlight here is, again, the peaks in these. Then maybe you could argue there's a little bit of a shift between them, but in general, the peaks in each distribution are at the same seasonal time, which is late summer, so August in the northern hemisphere and February in the southern hemisphere. And tropical cyclones are generally steered by the environmental flow in which they are embedded. So this is just a cartoon image here showing for the Atlantic is the progression of a tropical cyclone actually starting way off the west coast of Africa. So many of our tropical cyclones in the Atlantic form from disturbances that move off of the West African coast associated with the West African low-level jet. And it's breakdown into eddies. And so typically this large-scale flow, if you think of just a weighted average of the flow at 850 hectopascals and 200 hectopascals, so kind of an average of the lower and the upper troposphere, that gives you a pretty good guess at the motion vector of a tropical cyclone. And so we'd like to think of this as an analog to just like a rubber ducky floating down the river, is that you might think of tropical cyclones as being very large, but if you think about them in the context of the large-scale circulation of the atmosphere, they're actually relatively small. So it's they're just being pushed along by the large-scale flow. And so in general, the dominant steering feature in the tropics are the subtropical highs. That's what's shown here, the subtropical ridge. And that's not in every basin, but it's certainly in the Atlantic and the West Pacific basin. These are really important steering features governing where storms move. Okay, so I think it's nice to talk about, as an overview of tropical cyclones, to compare it to extratropical cyclones, which we've already talked about, and we think about much more on a day-to-day basis here. So pictures of each are shown on the right, and they're made to be approximately to scale. So extratropical cyclones are relatively large, a diameter of something like 1,000 to 3,000 kilometers across. Their structure is highly asymmetric, with precipitation focused primarily along fronts, which is to say strong temperature gradients across those fronts that are linear features. And the source of kinetic energy is the available potential energy stored within horizontal temperature gradients. So this is baroclinic instability, which we spent a lot of time learning about the theory of earlier in this semester. And they have a characteristic life cycle timescale associated with that instability, which is something like 3 to 7 days. So in contrast, a tropical cyclone is quite a bit smaller, though it can actually range across really an order of magnitude in sizes from a diameter of something like 200 kilometers up to 2,000 kilometers. The structure is circularly symmetric, with precipitation primarily focused in the eye wall, so just outside of the eye, so towards the center. So you don't have frontal features in a tropical cyclone, nor do you have strong temperature gradients, at least I should say focused with into linear bands like you do in extratropical cyclones. And the source of kinetic energy is self-induced heat fluxes from the surface, which we'll be going through in detail in this lecture. And the life cycle timescale is anything greater than a day. You can, in theory, a tropical cyclone, if you're given the right conditions, could last forever, or effectively forever. So that's one significant contrast from the extratropical cyclone. All right, so to understand why tropical cyclones exist within the climate system, you really have to understand a bit about how a tropical cyclone works. So this is something that really makes tropical cyclones particularly complicated to think about, is because you need to know what makes a tropical cyclone work in order to think about them more broadly within the climate system. So we're going to go through that here. So let's talk a little bit about the physics of the tropical cyclone. So we have to think a little bit more physically in terms of this. Let's think about this low-level inflow leg, and we're going to think about the rotating flow, which we'll call V here. So the azimuthal wind speed associated with the circulation. So in blue is that azimuthal wind speed, and so superimposed on top of this, as I put in red, really the more fundamental physical concept is what we call absolute angular momentum. So, or just angular momentum if you want for short. And this is a characteristic wind profile and angular momentum profile for a tropical cyclone. So you'll notice that you might think of this length scale out to this outer radius R0 in the bottom right corner of the left figure as to be something like 1,000 kilometers. So, but again, that can vary quite substantially. So absolute angular momentum, we can define it. This is angular momentum per unit mass. So that's typically thought of as radius times the velocity perpendicular to your radius. And so that really has two components, actually, for a tropical cyclone. So the cyclone part, which is the V here, so which is just the rotating wind field of the tropical cyclone itself, what you might think of, and that's probably a little more straightforward. But there's a second part, which is that associated with the Earth, is that the fact that you're on a rotating Earth, if you're not at the equator, you actually have a circulation velocity associated with the rotating Earth if you're a tropical cyclone. It's 1/2 F times R. And so the sum of those two gives you the full absolute angular momentum. That's why we use the term absolute, because you're including the Earth component. So what's interesting then is if you go out to this R0, where the circulation speed is 0, then all you have left is 1/2 F times R0 squared. We call this M0 because what this is your source of angular momentum for the system, is that because you're on a rotating Earth, you can have angular momentum even if you don't have any actual circulation flow velocity with your system. So this is the source of M for the tropical cyclone. And so now we're going to think a little bit about this inflowing air. So how are these things related to each other? So following this green arrow moving inwards, you imagine being an air parcel moving slowly inwards. So you're rubbing up against the surface. You're gradually losing angular momentum due to surface friction. So that's why this red curve and this red arrow, the red curve is going downwards towards 0. So you're losing absolute angular momentum, but you don't lose all of it. You only lose it at a certain rate. And so some of it you keep. And so as you move inwards, what you're actually doing is converting the angular momentum that you do conserve from the planetary component as R decreases into the relative component, which is to say the cyclone circulation, so RV. And so this is fundamentally how, just like a figure skater spinning faster as you move your arms inwards, this is the same concept here as angular momentum conservation. Okay, so now we have to think about this thermodynamically, and we have to bring in the thermodynamics and think about this just at a conceptual level here. So this is a diagram actually from my student Gia, from her work, is thinking about air moving inwards and now moving upwards in convection at small radii and then moving back outwards, and we're really focusing on the first two legs of that. And so really what's happening is, if you imagine starting at the beginning of this black overturning arrow, is that the air moving inward brings with it higher angular momentum. And so as it does so, you gradually increase the rotational wind speed. And as you increase the rotational wind speed, you enhance the surface heat fluxes. And as you do that, eventually you're gaining heat and to a point, and really gaining moisture in particular, to a point where you may become convectively unstable. So you can think about it in terms of equivalent potential temperature, if you will. You're gradually increasing your equivalent potential temperature until you become convectively unstable, and then you're going to rise. And so the thing is that this just goes back around in a loop, is that if you have air rising, then air needs to come in to replace it. And so you're going to draw more air inwards. And so this is a kind of a step-by-step mechanistic way to think about how the tropical cyclone works. But you just a warning here is this is a chicken and egg problem. You can't start at any one point in this and say that's the cause of anything. It's not right to say convection causes the hurricane. This is all a system that is sort of self-sustaining in a way. So this just lets you think mechanistically about what's going on. So I've highlighted this in blue here. This enhances surface heat fluxes. This is the energy source for the system. We're going to put equations to this in a moment. And the other part of this is that I mentioned this part about increasing the rotational wind speed. So that's enhancing surface friction. Yeah. And so because you have stronger winds near the surface, and that's going to be your energy sink. And so these are the things that are going to be battling each other. And we'll go through this quantitatively. So a tropical cyclone needs energy, and it needs angular momentum, two very fundamental quantities in our universe. It has kinetic energy and it's rotating, so it must have angular momentum. Those have to come from somewhere. So for the angular momentum, the source is the rotating Earth, as we mentioned, and the sink is surface friction. And then similarly, or I should say, then for energy, the source is surface heat fluxes, which we'll talk about, and then the sink is also surface friction. So, yeah. So let's focus on the second one, is the energetics, because this is really what's useful. We've gone a long way to understanding how tropical cyclones work by thinking about their energetics. So what can these energetics tell us about how a tropical cyclone works? So let's be quantitative and physical about this. So we're going to talk first about the general concept of a heat engine, which is a system that converts thermal energy to mechanical energy. So what does that mean? Is you're adding heat and you're using some of that heat to produce work. This is a very, very general thermodynamic concept. And we can put an equation to this. It says that you add heat at some rate. So these are in units of watts, which is an energy per unit time. So Q in dot is the heat rate. The rate of heat added to the system is equal to some rate of work done by the system. And then out front is a thermodynamic efficiency. So epsilon, which has to be less than 1. Fundamentally, by the laws of thermodynamics, this has to be less than 1. So we can actually use this concept. And so one way to think about this, that's really, I think, the easiest, is how we make our cars work, is you add fuel, and when you combust that fuel, it produces heat. And that heat is used to do work to move the car against friction. So friction tries to slow the car down, and you're using the heat from fuel, you're using that fuel to power the car forward. So what is this epsilon? So we're going to first talk about this thermodynamic efficiency in the context of our tropical cyclone. So a tropical cyclone we can actually think of as a natural Carnot heat engine. This is really a huge breakthrough in understanding the tropical cyclone. So this is a nice cartoon plot for where the color denotes moist static energy or entropy, or you can think of theta E. So blues are smaller values, reds are larger values. And superimposed on this is the overturning circulation associated with a tropical cyclone. So the inflow at low levels, the rising motion with the clouds, and so on and so forth. And so the key thing is that inflow acquires latent heat, or we'll say predominantly latent heat, to evaporation from the warm ocean surface, where the surface temperature is something like 300 Kelvin. And then the outflow loses sensible heat to space via radiative cooling at the cold tropopause, where the temperature is something like 200 Kelvin. And so in general, just to note, is that a heat engine requires adding heat, or really adding entropy at a warmer temperature, and losing heat or losing entropy at a colder temperature. So that's exactly what a tropical cyclone is doing. And that temperature difference spans the depth of the troposphere. So your heat is being added at the surface where it's warmer and lost aloft near the tropopause where it's colder. Okay, so, and for a Carnot heat engine, the thermodynamic efficiency is given by the difference between the warm and cold temperatures. So in this case, this is the sea surface temperature, Ts, and the outflow temperature, T naught, divided by the warm temperature, which is the sea surface temperature, Ts. So what's nice, this Carnot theory, the key component of this is that it lets us define a thermodynamic efficiency. So, and actually, if you plugged in numbers there, you'll get something like 100 divided by 300, which is a third. So that would mean a third of the heat input into the system could be used possibly to do work. So what is the heat source, and what work is the cyclone doing? What is this Q in dot and W out dot here? So let's start with the energy source, which is the upward surface enthalpy fluxes. And so we can write a bulk formula for surface enthalpy fluxes, which you may have seen in other classes or say in boundary layer meteorology. This is the simplest form for thinking about surface enthalpy fluxes in units of watts per meter squared, which is given by rho times the CK, which is an air-sea enthalpy exchange coefficient, times the near surface wind speed, that V, times the delta K is the air-sea enthalpy disequilibrium, which is to say the difference between the surface enthalpy, which is saturated, and the air overlying that surface. So what's really important in this equation is that heat fluxes increase with wind speed. And the physics of this, which might sound complicated, are actually something you are very, very well aware of. So for one thing, why do you blow on hot things? Is because you're actually enhancing the flux of heat out of the hot thing. So this is a sensible heat flux, as shown in the top right picture here. That's why you blow on your hot food or your hot drink. And then the bottom, though, which is probably more relevant specifically to tropical cyclones on Earth, is if any of you have ever gotten out of a pool on a on a windy day, I should say, not a cold day, you'll notice you get cold very fast. And that's because the wind greatly enhances the evaporation of water off of your skin, and that takes heat from your skin, and it uses the sensible heat in your skin to break the bonds of those liquid water droplets and convert them into latent heat stored in the broken bonds of the water vapor molecules. So it's the exact same concept, is that wind speed, larger wind speed means larger heat fluxes, whether sensible or latent heat. And now let's talk about the energy sink, which is frictional dissipation. I'm going to put this in parentheses. You can think of this as a downward surface kinetic energy flux, to put it in the same parlance as the energy source. And we also have a bulk formula for surface frictional dissipation, which is given by this equation here again, is density times a drag coefficient, an air-sea momentum exchange coefficient, times the near surface wind speed cubed. Again, has units of watts per meter squared. And I've highlighted here that you can write this in a much more intuitive way, which is rho CD times the wind speed times the square of the wind speed. And so what this makes it look like now is something that has a very similar form to the enthalpy exchange equation from the previous slide. And you can see now that instead of delta K, what you have is V squared, which is, if you think of the surface as being motionless, is a flux of kinetic energy into the surface. So it's a difference in kinetic energy between the surface, which is not moving, or at least moving very slowly, and the air overlying it. So you'll notice now surface friction, this equation increases with the cube of the wind speed, so even faster, but again, it increases with wind speed. And so it's a really simple analogy again, is think about falling off your bike and scraping your knee. The faster you're going, the faster you slow down, I guess, which is to say that surface friction, the surface kinetic energy flux is even faster, and you're probably more injured than you were if you were going slower. So putting this in physical terms is that friction removes kinetic energy from a near surface circulation, transfers it from the circulation to the surface. And so what that means is the system, meaning the tropical cyclone, has to constantly do work to regenerate the circulation. If you imagine the vortex is always rubbing against the surface, so it's always losing kinetic energy, so it has to be constantly regenerating that kinetic energy, and it's using the heat input to do that. So when you put these together, the surface is remarkably both the source and sink of energy for a tropical cyclone. So we can go back to our equation now, our Carnot engine view of translating or using heat input to do work. And so what we can do now is plug in our bulk formula for the heat input and the work done, which is so on each side of this. And what we're doing here, making an assumption that the surface fluxes scale with their values where the wind speed is largest. So we're in some sense ignoring radial variations, just saying wherever the winds are the strongest, so we call formally the radius of maximum winds, is the part of the storm that matters for the energetics. And so that's a good first order approximation. It may not be a perfect approximation, but it's a very simple one, and it makes our lives a whole lot easier. So if you plug these in, you get this equation here. And you'll notice what this does is you can now solve for Vmax, the maximum possible wind speed you can achieve given this system. And so the key thing is that there is a maximum because the heat input increases only linearly with the wind speed, whereas the work done against friction increases with the cube of the wind speed. So if you get too strong, then friction is much stronger, is too strong relative to how much heat input you're putting in. You can't do enough work to sustain yourself. So it's a stable equilibrium. So when you do that, you solve for what we call the potential intensity, the maximum potential intensity, which is really a thermodynamic limit on the maximum wind speed Vmax. And the seminal paper is shown in the bottom left if you're interested in more details. But you get this remarkably simple looking equation. Of course, you have to keep in mind what all these terms are, but you have as the square root of this Carnot heat engine efficiency times the ratio of the enthalpy and drag coefficients times the thermodynamic disequilibrium, the difference in the enthalpy between the surface and the overlying air, which is pretty amazing. And so let's, just to help to put some numbers to this, what's a characteristic value in the tropics? So delta K, so this difference in enthalpy is the difference in sensible and latent heat between the surface and the overlying air. So we talked a little bit about this earlier in the Walker cell lecture. So temperature differences are generally, and sensible heat differences are relatively small between the surface water and the overlying air, but the latent heat differences are large. So it's usually about an order of magnitude larger, the latent heat disequilibrium. So something like 10,000 joules per kilogram. So let's plug in some typical values otherwise. So the sea surface temperature is something like 300 Kelvin. The outflow temperature, the tropopause temperature is something like 200 Kelvin. Our exchange coefficients are actually both often assumed to be equal. So something like this, they're both small numbers, but they're equal. So you might set them equal to 1, the ratio, I mean. And then delta K is 10,000 joules per kilogram. So if you plug those numbers in to our equation, you get a nice simple answer of 60 meters per second. So you have, with a pen and paper, you can come up with an answer for how strong, an order of magnitude estimate for how strong a tropical cyclone could be in our present day climate. Okay, so let's look at a map of this. So we have this wonderful equation for potential intensity. And I'll note there's a couple of additional complexities associated with calculating potential intensity that I'm not going to go through here. So, but in general, this is a similar approach. So potential intensity governs where tropical cyclones can potentially exist. So again, this is the upper bound on intensity. So if the upper bound is say 0, you just can't have a tropical cyclone there at all. And so what's shown on the left here is the distribution of the 1979 to 2016 seasonal mean potential intensity, along with, and that's in the colors. So it's shown for July, August, September, October in the northern hemisphere, and December, January, February, March in the southern hemisphere. And the black dots denote genesis points during that time as well. And so on the right here is just showing you the same thing where you can see the earlier plot with the sea surface temperatures as well as the tracks, just so you can see as well that the tracks, how the tracks align with this. But so you can see the genesis points generally and the storm tracks generally lie in regions where this genesis or this potential intensity is reasonably large. So, and I'll say it also generally does a good job of explaining where the strongest storms on Earth are generally found, which is usually the West Pacific Ocean, because that's where the potential intensities are the highest. Okay, so some of you may have heard that wind shear is something that tropical cyclones do not like, which is true. So wind shear weakens a tropical cyclone, but it doesn't just do it directly. Our understanding of this is that it's predominantly done by transporting dry air, what I'll call anti-fuel, into the inner core of the tropical cyclone. So what do we mean by this? So this is going back to this nice transect of a tropical cyclone. What you're seeing in the colors is the distribution of moist static energy, or again, you can think of it as entropy more formally. And so at the core is you have a high energy core where the relative humidity is near 100%. It's nearly saturated. You have deep convective clouds and precipitation. And then outside of that is there's relatively low moist static energy air in the environment. So this is, again, remember, in the tropics in general, the free troposphere is actually relatively dry compared to, say, the boundary layer. And so what wind shear does is it actually generates eddies in the circulation. So it tilts the vortex. There's a couple of different pathways for this, but it tilts the vortex and just generally induces asymmetries in the circulation that can allow this low moist static energy air in the environment to get in. And so that's what this pink arrow is showing you, is it creates a transport of low energy or low entropy air into the core. And that's when we call it anti-fuel. What do we mean by that is that it really is sort of like a negative surface flux. Surface fluxes are a source of energy, and this wind shear import of low or of drier air is like a negative source of energy. So, and this process is something we call ventilation. So, and I recommend, if you're interested, checking out Tang and Emanuel 2010 and 2012 for the theory. This is pretty amazing. So at the end of the day, a tropical cyclone is affected by the combination of vertical wind shear and really the dryness of the surrounding environmental air. So again, this low moist static energy is predominantly a dryness, since the tropics can't really sustain large-scale temperature gradients. So I just want to also note the 3D dynamical and thermodynamic structure are really tightly coupled together. So this is probably not essential to this lecture, but I just want to highlight it for those of you who are interested, to give you more context on how a tropical cyclone works. So here's our rotating circulation with the overturning circulation superimposed on there. And so generally you can think of this as kind of a combination of, you have an inner deeply convecting region where air is rising and there's lots of precipitation. But then outside of this, air is actually very slowly subsiding. So this is generally an outer non-convecting region where air subsides very slowly, something like 2 millimeters per second in the current climate, as it cools radiatively. So, and so there's this very, very broad gradual subsidence outside of this narrow, strongly convecting inner core. So you might think of separating this into two different regions. And so what I'd like to do is to put this in the context of the near surface rotating wind. So you have to think, this is the y-axis here is not altitude here, it's the rotating wind speed. So this is, again, a kind of a characteristic wind profile and near the surface in a hurricane. So radius is on the x-axis. And so if we put this red dashed line on here to separate the regions, what you'll notice is in this inner convecting region is where you actually have very strong winds, but you also have very strong positive relative vorticity. So I have the much larger than zero here. It's very strongly positive, have very strong positive vorticity. Then you have this really broad region, and you have to remember too that this is a circle. So it's actually even the area is weighted by radius, if you will. So you have this broad annulus outside of the inner core that is actually has negative vorticity. and negative relative vorticity, but it's much weaker. It's not a strong, it's actually very, very small magnitude, but negative vorticity. And that dynamic outcome is actually very tightly coupled to the thermodynamics of this gradual subsidence in the free troposphere. Is that for those of you who remember your boundary layer dynamics, you're just geostrophic vorticity in the presence of friction, is that the Ekman suction or Ekman pumping rate is directly related to the vorticity in the boundary layer. So in this case, we actually have Ekman suction within the boundary layer in this broad outer region, which implies that its air is being sucked downward into the boundary layer, and that actually the rate of suction has to be equal to the subsidence rate in the free troposphere. So again, you have this very slow subsidence, which gives you a very weak negative vorticity because you have a very weak Ekman suction into the boundary layer. So those are tightly related. So what's interesting is there's another way to think about this radial structure of relative vorticity, which is via the Kelvin circulation theorem. Going back to your basic dynamics. So Kelvin circulation theorem says that the integral of the area, the integral of the vorticity over some area has to equal the circulation, which is the line integral of the velocity along that boundary. And so what does that mean in the context of our tropical cyclone is that if you say you define the boundary to be the outer radius, so here about 1,000 kilometers, where the wind goes to 0, this R0, the total vorticity in the cyclone within R at radii smaller than R0 has to equal the circulation around the cyclone at R0, which is 0, because we're picking R0 here to be where the radius where the rotating wind speed goes to 0. And so that's pretty cool because that says that, so for tropical cyclones, we generally think of them as a region of very strong positive vorticity, and that is definitely true in the inner core, but from Kelvin circulation theorem, that says that there then has to be negative vorticity that's equal and opposite in magnitude around it. And so that's exactly what's happening as the tropical cyclone has a much, much weaker in magnitude negative vorticity, but that's spread out over a much larger area in this outer circulation. So if you didn't have this, the cyclone would be totally unbounded, which is impossible. Okay, so that really covers the basic physics of the tropical cyclone. You can see there's a lot of components to it. Don't expect you to learn all of that at once, but trying to give you a good sense of the basics of its structure and its energetics. So now we want to move on to asking this question of why do tropical cyclones exist within the climate system? So going back to our initial statements of what is essential for a tropical cyclone, it needs energy and angular momentum because it's a vortex. And so we went through this distinction between angular momentum and energy, which you can think of as sort of dynamical and thermodynamic components for tropical cyclones, and it really depends on both. So how do these vary within the climate system of our Earth-like planet? So moving polewards, tropical cyclones are strongly supported dynamically. And so what do we mean by that is really, again, the statement that it needs angular momentum from the planet. So, and that comes down to F. So 1/2 F, we had said, times some radius squared. It's really F is the planetary vorticity that it needs. And so at the pole, it's a maximum. It's 2 times the planetary rotation rate. And really the one place where this is not sufficient is near the equator. So at the equator, F is 0. And so we can think of this in kind of physical conceptual terms, is at the equator, the axis of rotation of the tropical cyclone, which is the local vertical, is perpendicular to the axis of rotation. So remember, if you're standing on the equator, your body and your head is pointing directly out to outer space. And so your local vertical is perpendicular to the axis of the Earth's rotation. And so that means that there is no angular momentum available to you that projects onto your local vertical. So the storm doesn't have a source of angular momentum, or you can think of it equivalently as vertical vorticity. And so that's why they don't form too close to the equator again. Okay, so in contrast, thermodynamic variability is much more pronounced. And so moving poleward, tropical cyclones are strongly suppressed thermodynamically. So this is our plot from earlier in the lecture showing, again, sea surface temperature distributions and genesis points and tracks. And so at a very broad level, you can think of the tropics as being thermodynamically favorable for tropical cyclones. And then when you move towards higher latitudes, you become rapidly thermodynamically hostile to tropical cyclones. And so now putting this in the context of the physics of tropical cyclones that we talked about before is that as you move poleward, the potential intensity decreases quite rapidly. And this is the big thing, is that your air-sea enthalpy disequilibrium starts to decrease quite rapidly. And that is tied to decreasing sea surface temperatures. And then you also have rapidly increasing wind shear, which is a big part of this too, is you have the jet stream. So tropical cyclones do not like the jet stream. That induces significant wind shear. And so more generally, you can think of wind shear as tightly related to temperature gradients, horizontal temperature gradients. So tropical cyclones do not like large-scale horizontal temperature gradients, which is the polar opposite of extratropical cyclones. And this broadly applies in both the northern and southern hemisphere. So what about within the tropics? Can we think a little bit more about the variability? So within the tropics, generally you may have already noticed that potential intensity tends to be larger where water is relatively warm. And if you looked at, so on the left here is the map, the colors are potential intensity in meters per second. And then on the right is the colors for sea surface temperatures in degrees Celsius. And certainly if you just kind of glance at both of them, they seem to be very, very similar to each other, which is definitely true. They're not exactly the same, but they're very similar to each other. But I've underlined this point about it being relatively warm. This is the key thing I want you to take away here. Is so tropical cyclones really generally form where there is already persistent deep convection. And so as we've learned in the previous lectures, in the tropics, mean ascent, so persistent convection, occurs where sea surface temperatures are warmest. So this is not a statement about absolute sea surface temperatures. It's actually a statement about relative, or sea surface temperatures relative to the rest of the tropics, so the tropical mean. And formally, and I'm going to show this in the next slide as well, is potential intensity increases roughly by something like 8 meters per second per Kelvin of warming relative to the mean. And it increases only by something like 1 meter per second per Kelvin of absolute warming. So it is, and that's kind of all else equal in a simplified setting. So it's relatively warm. Regions that are where the sea surface temperatures are relatively warm are going to be where you're going to get deep convection, and that's where you're going to get you're going to have higher potential intensities, and you're going to be able to support tropical cyclones. And so two really nice examples of this to hammer home this idea that it's not the absolute temperature that matters, which is something you probably have heard many times. You just assume warmer sea surface temperatures mean much stronger hurricanes. So on the left here is a simulation of the last glacial maximum 21,000 years ago. So much colder. I think last time there was a glacial maximum, we had large-scale glaciers over the North America, for example. And so the top plot shows the distribution of potential intensity in colors. So the reds are higher potential intensities, and then the sea surface temperatures are in degrees Celsius are in the black contours. And then the bottom is the same thing, but for the last glacial maximum. So the top is the current climate. And you notice they look awfully similar to each other. And I'm going to highlight one specific contour in each. Is they look really, really similar to each other in their distributions, but you'll notice that it's almost like when you go back to the last glacial maximum, it's like all the sea surface temperatures are just decreased by 2 degrees. And that's a broad brush statement, but you're comparing here the 28-degree contour in the top plot and the 26-degree contour in the bottom plot, which are very, very similar in location and relative to where potential intensity is. So there's not really, so the absolute sea surface temperature doesn't really matter here. And so a second way to show this is you can look to simulations of very high carbon dioxide concentrations, which equates to much warmer climates. So what this plot, which is a relatively complicated plot, but we're going to go through it, is on the x-axis is sea surface temperatures, and on the y-axis is potential intensity, and what you're looking at is the joint distribution of potential intensity and sea surface temperature. So the contours are bounding generally where grid points of each of these values are found in a particular climate. So the black curves are a present day climate, and then the blue curves are a hot climate with CO2 concentrations something like 8 times what they are today. And then the red curves are a very hot climate where the CO2 concentrations are something like 20 times what they are today. And you notice that that shifts much to the right, so you're getting hotter and hotter. And so what I want to highlight here is, so first there's a slope to these curves. This says that within a given climate state, so within one of these contour sets, there's a slope, which is something like 9 meters per second increase in potential intensity per degree of relative warming, so within that climate. And you notice the slopes are actually remarkably consistent across each of these 3 simulations. And then second, you can compare then across each of these 3 sets. And you'll notice that as you go to warmer and warmer temperatures, these contour sets sort of shift to the right, but they don't really, they shift upwards a little bit, but not much. And especially going from the hot to the very hot climate, there's much weaker of a shift. And there's actually a saturation in in the dependence increase of potential intensity on sea surface temperature. So again, just highlighting that the absolute sea surface temperature is really, really not what governs where, or the maximum potential intensity of a tropical cyclone. So, okay, so I just want to come back to this idea about this strong thermodynamic suppression of tropical cyclones as you go poleward. And so what I want to do is to introduce a little bit of my research here, but I think it's a really nice way to think about this problem is to say, could we imagine a world where we just didn't have this thermodynamic variability? So if thermodynamic variability has such a strong effect on where tropical cyclones form, what would happen if we just took it out? And this is where models are really amazing for doing cool experiments to test our understanding of things. So I'll show you as these are simulations from a paper we published last year. So this is a simulation of an Earth-like climate. And what you're looking at are the colors are near surface wind speeds in meters per second. And then the grays are the continents. You're just seeing the wind speeds over the ocean. You'll notice a tropical cyclone in the Atlantic and another one forming there in the North Atlantic Ocean. And so what this is an Earth-like historical simulation from the last roughly 40, 50 years of a present-day climate state. And so you'll see tropical cyclones, but you see extratropical cyclones. You see these really strong surface westerlies in the southern hemisphere where nothing's getting in the way of those winds. So if anyone's ever been on a boat down there, it's very, very choppy. We get a whole lot of different phenomena, all the different phenomena that we've actually talked about in this class to date. So we can do something pretty cool is instead we can take our same model and do a totally different experiment where we take our planet and we have it rotating just like normal, but we cover it in water. So we take the land away and we also make that water the same sea surface temperature everywhere, which is here 29 degrees Celsius. And we make the sunshine, the solar insolation, constant everywhere on the planet, set it to just a constant annual mean of 340 watts per meter squared. So there's no seasonal cycle here at all. And this is something we call an aquaplanet with uniform thermal forcing. We're not the first to come up with this, to be clear, but we used this to do some cool experiments. And so right away, what is shockingly different, as hopefully you are noticing, is that the world looks very different. And you end up with a world actually where tropical cyclones now are not really tropical looking anymore. They're actually at all latitudes. And so what we've done is really made the Earth thermodynamically homogeneous, which is to say thermodynamically it's like the tropics, but now everywhere on the planet. But dynamically that's not the case because F still varies with latitude like it does on the real Earth. So what's pretty amazing is you get this world where without large-scale temperature gradients, we don't have a jet stream anymore. We don't have we don't have baroclinic instability. All we end up with is, for the most part, there's probably an MJO in here, but otherwise you have tropical cyclones covering much of the planet, particularly at high latitudes. But what's pretty amazing is they do actually still form generally at low latitudes. If you watch for long enough, you'll see cyclones form at low latitudes, and they actually move poleward and westward in time like they do in the real world. But instead of running into the jet stream or going over land or cold water, all those things have been removed. All the things that kill hurricanes have been removed. And so they sort of just pile up at high latitudes. And so the world could look very, very different if we didn't have this thermodynamic suppression of tropical cyclones as you move poleward. So if you want a way to think about this to kind of get your brain stirring is that this creates a world where you have a cyclone sparse equatorial belt and cyclone filled polar caps. And I'm happy to talk about this more with you separately with anyone who's interested, or you can also go and read the papers that we published last year on this, where we did experiments varying the rotation rate and size of this crazy tropical cyclone covered planet. Okay, so in general, we can say, and this is partly an outcome of the work we published last year, but I think what I'll talk about here is more general than that, is that tropical cyclones are really kind of fundamental to a thin convecting atmosphere like we have on Earth. So this goes way back thinking about what we mean by thin. Remember, is much shallower than it is wide. And we have a convecting atmosphere, particularly in the tropics. So what do these things mean, and why do we say this? So recall that for extratropical cyclones, so baroclinic cyclones, they extract available potential energy stored within horizontal density or temperature gradients. So we talked about these essential ingredients as being a horizontal temperature gradient and background rotation. So what about tropical cyclones? So tropical cyclones extract available potential energy that is stored within the thermodynamic potential, which is principally evaporative, so latent heat, between the surface and the overlying air. So what do we mean by that? So we're going to go back to a slide or a plot I had showed in a previous lecture. Is this idea that the relative humidity of the near surface air all over the planet is subsaturated. And so in particular, we had highlighted over the oceans, it's remarkably constant within the tropics, but even in general, it's something like 80% relative humidity. And that's really, really important. So why is that important? Is that really what we're saying is the near surface air is always subsaturated, which means surface water is always evaporating into the air, just like a puddle outside. And so that evaporation, that latent heat flux, has the potential, why we use the term potential, to be increased substantially. And specifically now you know how, which is by increasing the wind speed. So if the wind speed is faster, you're going to have a larger latent heat flux, or more rapid evaporation. And so really a tropical cyclone has figured out a way to do this for its own benefit, which is pretty amazing. It combines the dynamics associated with a rotating planet and the angular momentum that you get from the rotating planet to generate the wind speeds and creates a system in which those wind speeds can increase the surface heat fluxes and create a feedback within that system. So this is really pretty remarkable. So we can go one more step, which is, so why is this near surface thermodynamic potential there in the first place? Why do we have subsaturated air? Or why is there a difference? Why isn't the air, the properties of the air, the temperature and moisture, why isn't it just exactly the same as the surface beneath it, particularly over the ocean? So we can actually think about this in a conceptual and quantitative way. So consider this is a column of atmosphere, or you could think about it as the average tropics as a whole if you want to, with the ocean surface at the bottom and then an atmosphere above it. So this thermodynamic potential will exist in any convecting climate system whose surface is heated and whose overlying atmosphere is cooled. And that can be via net radiation. So when you talk about radiative convective equilibrium, we thought about just net radiation. It could also be through advection. So you could have a net heat transport out of the column. Whatever it is, you're heating the surface and you're cooling the overlying atmosphere. And at equilibrium, what that means is if you're going to reach an equilibrium where temperatures stop changing, there's a missing link here from the surface to the overlying atmosphere, which is that you require an upward transfer of heat from the surface into the atmosphere. So the surface is being heated, the atmosphere is being cooled, you need a transfer of heat from the surface to the atmosphere. And these are these enthalpy fluxes, these latent and sensible heat fluxes from the surface. So to have any latent and sensible heat fluxes from the surface, you need to have a difference between the overlying air and the surface. So you need a thermodynamic jump of latent or sensible heat between the surface and the overlying air. And so that's really the fundamentals of just thinking of this in terms of a climate system. Any type of convecting atmosphere is going to have this property. It does need to have a surface. Maybe it doesn't have to have a surface. We're not sure, but how we think about this is you have a surface. So just an additional note is, why does the atmosphere have to be convecting? You can think of this in terms of potential intensity theory. Is this thermodynamic efficiency for the Carnot heat engine has this difference in temperature between where heat is added and where it is lost. And so you need that temperature difference across the depth of the atmosphere, from the surface to the tropopause. So that's where deep convection is really important, as part of this, for creating a temperature difference between the bottom and the top of this, or the where heat is added and where it is lost. All right, and one additional fun note that I think fits nicely in with a lot of what we've talked about here is to emphasize to you that tropical cyclones do not actually require a condensable species, such as water. So often it is stated that tropical cyclones are powered by latent heat in convection, and that doesn't have to be true. It is, I wouldn't say it's true on Earth either, but at least in our current Earth climate, we have our tropical cyclones are moist, and so latent heat release is a part of that energetics, but it's really surface heat fluxes that matter. So what I'm showing you here is a simulation. This is from recent work with a colleague of mine we published last year, called Dry and Semi-Dry Tropical Cyclones, where on a simulation on an F plane, so F is constant, and we've actually set it to an artificially high value, note there, that just makes the storm smaller. In a doubly periodic box, so it means that stuff going out laterally in any direction just pops out on the other side, with fixed surface temperature. So I'm not saying sea surface temperature here, I'm just saying surface temperature, because it'd be varied how wet or dry the surface was. And in this case, this is a dry surface. And with an atmosphere that's just cooled at a constant rate. So it's meant to mimic a very simplified form of radiative cooling of the atmosphere. And that's initialized with random noise. And then in this world, cyclones form spontaneously. And so what you're seeing here, what's colored, is the wind speed near the surface. So you'll notice, you can see it, get a sense of this rotating circulation with these systems. There's a bunch of little vortices in here. And so I'll note that fixing the surface temperature basically acts like a constant heating from the sun, if you will. And so what these are dry hurricanes. So you wouldn't, if you looked at precipitation, you would see nothing at all. And you'll notice that they're actually, they look quite variable. They're generally weaker and more variable than their moist counterpart. They're quite turbulent. So you don't really get a nice clean circular eye with a nice clean circular eye wall. It seems to be a little bit messier. And these are fueled by sensible heat fluxes rather than latent heat fluxes. So there's a big temperature jump between the surface and the overlying air, because there is no moisture jump there, because there's no moisture at all. So again, something I'm happy to talk about more separately, or you can go and check out the paper. This is pretty cool. And I'll say there's still a lot of things about these dry cyclones that we do not actually understand fully still. Okay, I'm just going to end with this class is on large-scale circulations. So a question you might wonder is, so is a tropical cyclone considered a large-scale circulation? And I'm not going to answer that. I'm just going to say yes and no. And just emphasize why I asked this question is really its physics are very different. They operate very differently from the traditional waves and eddies that we've talked about, which is also, to be fair, true of, say, the Madden-Julian oscillation. But in this case, this is really the cyclone that's able to enhance its own energy source internally. And so you could think in both directions in this. I'm not going to say any more. Just say you can decide your own opinion. Think about what you think it means to be a large-scale circulation and whether or not that fits in with a tropical cyclone. Okay, go to Blackboard to answer a few questions about this topic.